All right, in this section 7.4, we're going to be doing the Laplace transforms inverse. So I know so far we've done two whole sections, and I still haven't really talked about why we need the Laplace transformation. So what I'm going to do now, and what the book does, is just show you why. So here we go. Given some differential equation y double prime minus y is equal to negative t, with initial conditions y of 0 is equal to 0, y prime at 0 is equal to 1. So we have this initial value problem and we want to solve it. We can easily solve this from the chapter 4 stuff we were doing before. We would do the auxiliary equation to find the homogeneous solution. We would also have to do some undetermined coefficients to find the non-homogeneous particular solution and then add those two things together. Then after that, we would have to find the constants using the initial conditions. It's definitely doable. It's not hard. It would just take a lot of time. But let me show you how easy it would be just doing this with Laplace transformations. So what we're going to do is we're going to take the Laplace transform of both sides. All right, so just to write it all out, bear with me for a second. We're going to take the Laplace transformation of the second derivative of y minus, we're going to do the Laplace transformation of y itself. That's going to be equal to, I'll just write it as the Laplace transformation of negative t of the right-hand side. So just taking the Laplace transformation of every single term in my differential equation here. Okay, so we can do each of these. Remember that we saw a theorem about taking the Laplace transform of a derivative. Here we have the second derivative. This, going back to the last video, or you can just look up the formula in the book, is going to be s squared. Tripped over my words there, sorry. So s squared, the Laplace transform of just y, and it's going to be minus s times y at 0 minus s to the 0, which is 1, y prime of 0. So these three terms is the Laplace transformation of the second derivative. And again, there was just a formula for that. That's still going to be minus the Laplace transform at y, so that's just copying it down from the equation above here. And that's going to be equal to the Laplace transform of negative t. That is one that we've actually seen before. I'm going to go to the book here at the table. Remember, you have a t to a power. This is t to the 1. So for us, it's going to be 1 factorial, which is just 1, divided by s to the 1 plus 1, so s squared. Just don't forget this negative sign we're factoring out. So the Laplace transformation of negative t is negative 1 over s squared. And again, we're just getting that from that table in the book. Cleaning up the left-hand side here and plugging in the initial conditions, we're still going to have s squared. And then the Laplace transform of y, and we have this minus Laplace transform of y. So I'm going to combine that together. So this is going to come out to be s squared, whoops, sorry, wrong button, s squared minus 1, and then this Laplace transform of y. Okay, minus s times y of 0, so that's the initial condition, so this is going to be s times 0, and then minus the first derivative of y at 0, which is 1, and that's still going to be equal to negative 1 over s squared on the right-hand side. Okay, and we can clean this up a little bit more now. So this is, of course, just going to be 0, and then we can add the 1 over. Oops, sorry. I'm going to, no, I'll just write it out. Laplace transform of y. So we still have this s squared minus 1 Laplace transform of y, but that's going to be equal to negative 1 over s squared, and we've added the 1 over. We are going to combine these two together by getting a common denominator of s squared. So just to combine them and add them together, think of this 1 as s squared over s squared. We'll end up with s squared minus 1 divided by s squared, just combining these two things together. Okay, then we're going to divide by the s squared minus 1 on both sides, and we end up with the Laplace transform on the left of y is equal to just 1 over s squared on the right-hand side. All right, so we have now solved for the Laplace transform of y. If we had a way of taking the inverse of this, we could just get y itself. So if we could take the inverse of the Laplace transform, which I'm going to show you how to do here in a minute, we could solve this. In fact, we should know, just because of this up here, right, when we had the Laplace transform of t, it was 1 over s squared. So if the Laplace transform is 1 over s squared, then we just undo that. So the Laplace transform of t is 1 over s squared. Thus, that says that my function y is just going to be the function t. And that is it. That's the final answer. And not only is that the final answer, but that's the final answer for this set of initial conditions. Notice how short this was compared to all of the stuff we'd have to do with the homogeneous and the non-homogeneous and the plugging in the initial conditions. This Laplace transformation helps us solve these differential equations a lot quicker than before. And not only does it let us solve them a lot quicker, it lets us solve differential equations that we couldn't have solved in other ways. All right. Before we get to more examples, let's just write out a few things. So a definition here. Given a function, now remember this capital F of s represents the Laplace transformation. So this is the Laplace transformation of some function. Given that, if there is a function little f of t that is continuous on that interval that we always do, 0 to infinity, and it also satisfies the normal definition for the Laplace transformation. If I were to take the Laplace transformation of this little f of t, it would give us that big F of s. Okay, so if that's the case, then we say that little f of t is the inverse Laplace transform of big F. And we use the notation, and I hope this notation is pretty obvious, but we do the Laplace inverse of capital F. Okay, so this represents little f of t, right? The Laplace transform. The inverse Laplace transform of the Laplace transform just gets us back to the original function. And there's not like an easy way to do it. It's mostly based on that table from before. So just to bring up that table in the book, instead of looking at the left-hand side and getting the Laplace transform, we're going to be looking at the right-hand side and undoing that to get back to the function itself. So let's just do a few examples of that. We'll do like maybe 3 of them. Okay, so the first one, so all we want to do for these is we want to determine the inverse Laplace transform. The first one that we want to try is, let's say that the Laplace transform is 2 over s cubed. Okay? So if that is the inverse function, we're going to go to our table, and we want to look at the right-hand side to see if we can find anything that looks close to 1 over s to some exponent. And it looks like the only one that would make sense is this third one here. So I have a constant up top, some n factorial thing, but I can make this to be an s cubed in the denominator. The problem, right, is that we don't have that 2, is that we don't necessarily know if the constants are going to match up. But we can always fix that after the fact if need be. So we want to take the inverse Laplace transformation of 2 over s cubed. And we write it like that, right? This is going to be a function of t after you do the inverse. Okay. Okay, so just to rewrite this, let's try to rewrite that in that form that we saw in the table. So this is going to be the inverse Laplace of, we're going to write it 2 up top is the same thing as 2 factorial. That s in the bottom, I could rewrite that s as s to the 2 plus 1. This and this are the exact same thing, but now this is in that format where my n is equal to 2. So if I go back over to this page, if I substituted in n to be 2, that would give me t squared. So in other words, the Laplace transform of 2 over s cubed, t squared. Okay, maybe one more quick example, or two. So let's say that you had the function, the Laplace transformation, capital F of S is 3 over S squared plus 9. Okay. So if we wanted to take the inverse Laplace transform of this, 3 over S squared plus 9. We're going to go into that table in the book. The homeworks are really nice because it gives you a button that just lets you open up this table directly. But we want something that looks somewhat in this format. We have a constant up top and then S squared plus some other constant here in the bottom. So going to our table, it's looking like it has to be this one, right? Because the cosine has the S in the numerator, but we do not have an S in the numerator. We have a constant up top. And look, it even matches up, because remember we had a 3 up in the numerator, and then down here that 3 squared 9 was in the denominator. So it looks like it has to be sine, where my b is equal to 3. So really just to rewrite this out, one more line. You don't have to do this if you don't want to, but we have the Laplace transformation, and we're going to rewrite it in that format. 3 divided by S squared plus 3 squared. Then just the inverse of that was sine of 3t. So that's going to be my answer here. All right, there is one other trick that I want to show you of stuff that may show up, and definitely something that you guys are going to have to do. So let's say we have something a little bit more complicated. The Laplace transformation, s minus 1 over s squared minus 2s plus 5. We want to do the inverse of that. Okay, so again, just to write it all out, right, we're going to do the Laplace inverse of, just to copy it down, s minus 1 divided by the s squared minus 2s plus 5. Okay, if I look in the table, so I'm moving over to the table, notice that I don't really have a quadratic in any of these denominators, but down here, it's kind of close, right? If I were to multiply these out, it would be a quadratic. So what we're going to have to do, which is everybody's favorite thing, is we're going to have to complete the square. If we do complete the square, we're going to get things that are in this form. We just don't know which one it's going to be yet. So let's complete the square of this denominator over here. So just to write it all out, still the Laplace inverse. We still have that s minus 1 in the numerator. But now in the denominator, we're going to leave the s squared, we're going to leave the negative 2s, but now we're going to add on the completing the square step, which is to take half of the negative 2 and square that. Half of negative 2 is negative 1, but squaring a negative 1 makes it a positive 1. We still have this plus 5 that's going to come over. Now we just added a 1, which means we also have to subtract a 1. That way it cancels out. The reason we do that is now these first 3 terms represent a perfect trinomial. So again, just writing it all out, we still are looking at the Laplace inverse of, we still have that s minus 1 up top, but now in the denominator we're going to rewrite that. S squared minus 2s plus 1 is s minus 1 all squared, and then plus 5 minus 1, which is plus 4. Okay. Now let's go back over to our table and see if this matches anything. We have an s minus 1 up top, s minus 1 squared, and then a plus 4. So it looks like it's matching to this bottom one down here. S minus our a value is going to be 1, plus, this was a 4 in our example, so we're going to have to take the square root, which is going to be a 2. So it's going to be e to the 1t times cosine of 2t. And we just write that out. So e to the t cosine of 2t as our final answer for the inverse Laplace transformation. All right, we're going to do a couple more examples of this after we look at some theorems here in the next video.